So as promised, when we finish the syllabus, if we had time, and we have, here's a review of ionic equations. This is particularly useful if you're going on to study chemistry post GCSE, because you will be expected to know what an ionic equation is when you work on probably the redox topic and also obviously for quantitative chemistry. Now there are three places you will come across ionic equations and have done in the syllabus. There's the reaction of acids and alkalis, there's displacement reactions, and in the very last topic we came across plenty of ionic equations for the precipitation reactions. Now ionic equations are used to emphasize a change, and this is particularly the case if you do redox chemistry later on. Ions that don't change don't appear in the ionic equation. They've got a special name, they're called spectator ions. Typically, they will be aqueous ions at the start of the reaction and they'll finish up as aqueous ions. What we need to particularly watch out for in the precipitation reaction is aqueous ions becoming solids. So we'll start with neutralization. Now we should all know that it's the hydrogen ion that gives an acid its characteristic properties, H+, and it only behaves as an acid as far as we're concerned when in aqueous solution, so H plus AQ. And the ion which gives an alkali its characteristic properties is OH-, again in water, so OH- AQ. Now if you put OH- and H+ together, you've got two H's and one oxygen. You've got, now what could that be? OH2O. That was tricky, wasn't it? So now all you need to do is put, for the ionic equation for all neutralization reactions, H plus AQ plus OH minus AQ going to, so arrow, H2O liquid. And that represents every single ionic equation for neutralization. Simples. Okay, you don't need to bother with the ions that make up the salt. They are spectator ions. They float around in the solution at the start of the experiment and they float around in the solution at the end of the experiment. So here is an alternative and perhaps more long-winded way of arriving at exactly the same answer. If we consider the reaction between nitric acid and potassium hydroxide, there's the symbol equation, and you can see the importance of the state symbols here, these aqueous. That means they are made up of free ions. Ions by free ions, free to move in the solution. So if I write every substance that's made of free ions as its separate ions, then you'll see what you get. Notice water is not made up of free ions. Water is a simple molecule. Now, just as in maths, if this was an equal sign, you'd cancel out. So I can do exactly the same thing here. I can cancel out K plus aqueous. It appears on each side. I can cancel out NO3 minus aqueous. It appears on each side. And then what am I left with? Oh, exactly the same answer. Okay, so whichever approach, that is the ionic equation for neutralization. Okay, if you try exactly the same approach for the reaction between sulfuric acid and sodium hydroxide, you will get exactly the same answer. Just need to be a little bit careful when you write the balanced symbol equation for that reaction. Remember, it's H2SO4 and sodium hydroxide NaOH, so you need two NaOHs. So you'll have two H pluses in the sulfuric acid, but you'll also have two OH minuses from your two lots of sodium hydroxide. So what about the reactions between acids and carbonates and acids and metals? Well, again, you can use this quite long-winded approach if you wish, but also you can simply think about, well, the important ion in an acid is H+. The important ion in a carbonate is CO3 2-, and the products, excluding the salt, are H2O and CO2. So, for the reaction between an acid and a carbonate, it's 2H+, aqueous, plus CO3 2- aqueous, going to H2O gas and H2O liquid and CO2 gas. Again, you can use a similar approach if you wish for acid with metals. For instance, with magnesium, the important ion in an acid is H+ again, and it reacts with a metal. The metal is not metal ions, it's metal atoms. And what happens in this is that you form a salt plus hydrogen. Now the salt is a little bit more important here than in the previous examples, in that it contains now metal ions. So if I take magnesium, 2H+, aqueous, plus Mg, goes to H2 gas plus Mg2+. So it was metal atoms to start with in the metal itself, but becomes metal ions, so it needs to be included in the ionic equation. The non-metal part of the acid, sulfate, nitrate, etc., doesn't appear at all in the equation. So displacement reactions, there are two types of displacements. Those involving metals. Magnesium will displace copper from copper sulfate because magnesium is more reactive than copper. What we need to understand here is that the magnesium is magnesium atoms, but in the compound here we've got copper ions, and these go on to form copper atoms and magnesium ions because the magnesium goes into the compound. And the other ones we need to look at are non-metal displacements. Chlorine is more reactive than iodine, so we'll kick it out from potassium iodide. And you can use exactly the same approach, starting with a balanced symbol equation. So for the first one, it would be Mg plus CuSO4 going to, etc. You can write that yourselves. Then, which substances are made up of free ions? Well, the copper sulfate is made up of free ions. So, Mg plus Cu2 plus aqueous plus SO4 2- aqueous goes to Mg2 plus aqueous plus SO4 2- aqueous plus Cu solid. I should have said the magnesium at the start would be solid as well. So you can see, I hope, that the only thing you can cancel out there are the sulfate ions. So you end up with Mg plus Cu2 plus all aqueous, Mg solid plus Cu2 plus aqueous going to Cu solid plus Mg2 plus aqueous. Now what about for the other one? Well, running through that one, you have Cl2 in aqueous solution. That is not made up of free ions. Chlorine is a non-metal, so it's made up of small molecules. Potassium iodide consists of 2K plus to make it balanced plus 2I minus, both aqueous, and we go on to form I2 in solution plus 2K plus plus 2Cl-, both aqueous. And the K pluses cancel out on each side, so you should be left with what you can see at the bottom of the screen there. Precipitation reactions. We did a lot of work, or a fair bit of work, on this in the analysis topic, and I would suggest that if you're struggling on some of the answers to these questions on this slide, then you go back and have a look at your answers in the analysis topic. But there are two types here. There are essentially those for metal ions, when we're testing for metal ions, where you add sodium hydroxide, and some of the non-metal ion tests. Again, you can use exactly the same approach. Split everything up into ions that is ions. Remember, the precipitates that you form are not free ions. They are solids. The ions are stuck together in a lattice. So you need to think about, in each instance, what the precipitate being formed actually is, and that makes life quite a bit easier. So again, start with the balance symbol equation. If you want, cancel out once you've written everything as free ions. Remember, the precipitates are not free ions. You can do it another way, using the idea of key ions from the reagent that you're testing with, and obviously the one you're testing for. So we'll start with sodium hydroxide. Obviously, the key ion in sodium hydroxide is the hydroxide ion, OH- aqueous. And well, this will depend on which actual substance you're testing for. And so what you need to be aware of are those four little steps. And of course, add state symbols. So let's say we were testing for magnesium ions. The formula of the ion you're testing for, Mg2+. The formula of the key ion in sodium hydroxide, OH-. Now Mg2+ requires two OH- to complete the formula of magnesium hydroxide. So the formula of magnesium hydroxide is Mg in brackets OH twice. So that means you need a 2 in front of the OH- aqueous to balance the equation. State symbols, well, your metal ion will be aqueous, sodium hydroxide is aqueous, and the MgOH twice is of course a solid. So that will work for every single example you need to know. Watch out for FeOH 3 times for iron 3 hydroxide. Most of the ones you need to know, though, are simply follow the pattern MgOH twice. Testing for non-metal ions, you need to use exactly the same approach. The key ions in the reagent. Well, when we're testing for a carbonate, we've already done or mentioned this one. 2H plus CO3 2 minus, both aqueous, goes to CO2 gaseous and H2O liquid. It's the silver ion that's important when you're testing for chloride, bromide and iodide. Ag plus aqueous plus Cl minus aqueous goes to AgCl. The precipitates silver chloride, silver bromide and silver iodide all follow that same sort of formula. Of course, they are solids. And then in the sulfate test, Ba2+ is the important ion in the barium nitrate or barium chloride, whichever you use, and that reacts with the sulfate ion SO4 2- to form BaSO4 solid. So it's simply Ba2 plus aqueous plus SO4 2- aqueous going to BaSO4 solid. Now that is everything as promised. I'll be giving you back your tests as soon as they're all marked, so you've got those to review, and also from the 11th of May I will be setting some pre-IB/A level work.